Hi, so this video has the somewhat ominous looking title of the central limit theorem, but it's actually not that crazy. It's just about how things add up, which is not that hard at all. So the first thing I want to convince you is that normal distributions are amazing because of how they add. So in contrast, if you take two uniform distributions and add them together, the distribution of the sum is not uniform. It's actually triangular, which is actually quite hard to prove. But mathematically, that's what you're going to get. You're going to get a triangular distribution, not another uniform distribution. But normals are great because if you add two normals together, the result is normal. So let's say I have these two normal distributions, these two variables, and I add them together, then the distribution of their sum is normal, and quite intuitively, you just add the means and add the variances. It's actually really simple. Okay, but I want to do this a bit more formally. So let's say I have two variables, x and y, and they each have their own mean and their own variance. And so I put the little subscript x for the x variables and y for the y mean and variance. And let's say there's a variable z, and z is ax plus by plus c. And sorry if that's confusing. I don't mean the z distribution. I just use the next letter in the alphabet. I don't mean the z distribution. I just used that letter by accident. Anyways, z is going to be normal, and it's going to have a mean where you just plug the means in. Very intuitive. But the variance, you actually square the coefficients. You square a and b before you plug in the variances. And c actually isn't even a part of that at all. Okay, so the variance is a little bit different. You square those coefficients. So let's see how this all works. So I'm going to do questions about rainfall. And I'm going to use three variables. You might want to take a second to write these down because I'm going to use them a lot in the next few problems. So J is rainfall in July with this mean in SD. A is rainfall in August. And S is the rainfall in September. And yeah, take a second, write down these numbers because I'm going to be using them in the next few examples. Okay, so I'm going to start with the probability that the rainfall for all 3 months is greater than 225. So that's what I'm doing. J plus A plus S is greater than 225. Well, J plus A plus S is normal, and you just add the means together, add the variances together, piece of cake. So the sum of rainfall is normal with a mean of 240 and a variance of 769. Note that's the variance, not the SD. You have to square root that to get the SD. So finding z, I am going to subtract both sides by the mean and divide by the SD to create z. And that gives me negative 0.54. So go to the z table, and I'm going to look up 0.54. And I got an area of 0.7054, and that's the answer. Because from the top, remember the trick that if you change from negative to positive, you change the direction of the inequality. Anyways, the answer is 0.7054. Okay, another example with rainfall. Okay, I want the probability that the total rainfall for September is greater than the total of July and August. So I'm doing this. Now, it's no good to have variables on different sides of the inequality, so I'm going to move J and A over to the left. And that's important because I have now a number on the right. Okay, so I need to find the distribution of S minus J minus A, which technically is S plus negative 1 times J plus negative 1 times A. And that's important because in the variance, I'm going to square the negative ones. And actually, I'm going to add the variances together. I'm not going to subtract the variances because those negative ones will be squared. Okay, so I have the same variance as before, but now the mean is negative 40. So calculating this out, I'm going to subtract the mean from both sides and divide by the SD. And again, minus 40 makes positive 40. So I want the area greater than 1.44 in the z table. So looking up 1.44, that's an area of 0.9251. Subtract that from 1 because I want the area to the right, and the answer is 0.0749. Okay, one more question about rainfall. This one's pretty messy looking at the beginning, but just stick with it. I want the probability that the rainfall for all 3 months, the average of all 3 months, is less than the rainfall of August. So that's this statement. The average is less than August. And again, it's no good to have variables on both sides, so I'm going to move the a over. I'm going to simplify the fraction. I'm going to break it up and simplify the numbers. So it's going to be 1/3 j minus 2/3 a plus 1/3 s. And I want the probability this is less than 0. So I have to find the distribution of 1/3 j minus 2/3 a plus 1/3 s. And it's normal with the mean and variance you see here. So you square the coefficient in the variance. So the negative 2/3 is going to be squared, and it's going to be positive. It's going to all be added up together. And 1/3 j minus 2/3 a plus 1/3 s is normal with a mean of 5 and a variance of 1,444 over 9. That's what it all came to, all that work in the last slide. All right, so making the z, I have to subtract the mean of 5 on both sides and divide by the variance, which is the SD, which is the square root of the variance. And what I end up with is z less than negative 0.39. So go to the z table, look up 0.39. And the area to the right is therefore 0.3483, and that's the answer. Okay, so normals add up to normals, which is great. But there's more, and this is actually what the central limit theorem is talking about. You can have any kind of random variable. It could even be discrete, not even continuous, but if you have a bunch of them, then the distribution of their sum converges to a normal distribution. And that is what the central limit theorem says, or the CLT. So here's a more formal definition of the CLT. Let's say I have a bunch of variables. I have n of them, and they all have the same distribution. And again, the distribution could be binomial, Poisson, any kind of discrete distribution, any kind of continuous distribution. It doesn't matter. All that matters is they all have the same distribution, which means they all have the same mean and the same variance, mu and sigma squared. So if n is large, then the sum is normal with a mean of n times mu and a variance of n times sigma squared. And in consequence to that, the average of the variables, the distribution is also normal with a mean of mu over n and a variance of sigma squared over n. And that's actually a result that we're going to use a lot of in the future. We're not going to talk that much about sums, but we're going to talk a lot about averages. So that's a very important result. Okay, so let's use it. We're going to roll 100 dice and add them all up. And we did this in class, I believe, but the distribution of one dice roll is this, and the expected value is the mean of 3.5, and the variance is 35 over 12. Okay, so that's the mean and variance of all 100 dice rolls. So the sum is normal with the mean of 100 times 3.5, or 350, and 100 times that fraction. So I have the mean and variance of the sum. So turning this into z for the table, the probability that the sum is bigger than or equal to 375, and let's also stop for a minute and make sure we do the continuity correction, because dice can only be whole numbers and the normal is continuous. So this is greater than 374.5 with the continuity correction. Then I'm going to subtract the mean on both sides, which is 350, divide by the SD, which is the square root of the variance. And this gives me z greater than 1.43. So go to the z table, look up 1.43, and subtract that from 1, you get the probability of 0.0764, and that's your answer. It's kind of unlikely. Okay, another one. Okay, so we have a roulette wheel again. You're going to play $5 on your favorite number, and little explanation is required. Again, there's 38 possible outcomes. Only one of those outcomes is your number. And when you bet in roulette, if you win on a number bet, you actually win 35 times your bet. So if you win, you're going to win $175. However, if you lose, then you lose the $5 bet that you made. So this is a fairly simple calculation. Let's find the expected value and the variance of this distribution. So the mean is negative 0.263 with a variance of 830. So the sum of all 400 bets is going to be normal because n is quite large, with a mean of negative 105 and a variance of 33,000. Nope, that's 332,000. So you're going to expect to lose $105 by playing this game 400 times. But moving on, I want the probability that by the end of all of this that I will lose money. And I'm not going to worry about any kind of continuity correction. Technically, my money goes up and down in increments of $5. But I'm just not going to worry about it. I want the probability that the sum is less than 0. So subtract the mean from both sides, divide by the SD. This is the probability that z is less than 0.18. Go to the z table, and the answer directly is 0.5714. Okay, so this is now getting some really useful kinds of questions and how it comes back to the normal. So we'll do more of this in class. I'll see you then.